Hey everybody, in this video I'll be explaining some things to you about moles. And moles are a concept that chemists have developed to compare things that you cannot see or that are too small to measure, like atoms, to things that you can measure and see, like grams or liters of a gas, grams being the mass of a solid or liquid. And so the idea here is that a balanced chemical equation describes how substances react, but the numbers that go in front of them as coefficients or after an element, the subscripts, describe how many atoms or molecules or formula units of those substances are reacting and participating in that reaction. And so there needed to be a way to compare things that are too small to measure, atoms, to the measurements that we can make, like mass of a solid or a liquid or volume of a gas. And so even in the smallest grain of salt, there exist trillions upon trillions of atoms. And so to try to measure out a specific number of atoms, like if a reaction had one atom of this element reacting with two atoms of this, would be too difficult to measure out. And so we need to have a concept, a way to compare number of atoms to the things that we can measure, like grams of a liquid or solid, or liters of a gas. And that's the mole concept. Now, this whole idea about moles, again, was really to relate atoms or subatomic particles to things that you could measure, like mass in grams. And what chemists decided to base this on was a very common element, carbon. And the most common form of carbon they knew was called carbon-12. And they also had known that carbon-12 has 12 things in its nucleus that contribute to its mass, 6 protons and 6 neutrons. And so what chemists were trying to do was connect how many atomic mass units an isotope or a substance has to the number of grams. And so they said, well, let's say that something with a certain amount of atomic mass, that 1 mole of it will be however many atoms or molecules or formula units it takes to have that many grams of it. And so there were some experiments done to figure out, with carbon-12 having an atomic mass of 12, how many atoms of it are in 12 grams of it. And it turns out there are quite a lot. There are this many carbon atoms in 12 grams of carbon-12. And so chemists decided to call this number 1 mole. So this number is how many atoms, how many molecules, how many formula units, how many things are in that many grams of that substance which has that many atomic mass units. Now this can be simplified using scientific notation to 6.02 times 10 to the 23rd. And to relate this not just to carbon-12, but to other substances on the periodic table, as well as compounds that contain many elements, the mass of something, its molar mass, is how many grams have this many atoms. So the molar mass is how many grams of a substance has this many either atoms or molecules/formula units for a compound. So for example, the atomic mass of carbon is 12. And so in 12 grams of carbon, there are this many atoms of carbon. For all elements, the number of atoms, this number, 1 mole of atoms, is equal to their atomic mass in grams listed on the periodic table. So manganese, for instance, its atomic mass is 54.938 atomic mass units. We also could change those units to be 54.938 grams per mole of manganese. And so that means that in 54.938 grams of manganese, that there would be this many atoms of manganese. For compounds, though, because they contain atoms of more than one element, it is going to be the sum of the atoms in them will be their molar mass. And so, for example, magnesium chloride, its formula is MgCl2. Its molar mass would be equal to the atomic mass of magnesium added to the atomic mass of chlorine times 2. So in 95.210 grams of magnesium chloride, that is 1 mole of it, and there are this many formula units of magnesium chloride. So there are this many magnesium atoms and twice this number of chlorine atoms. Now this statement that I wrote down is called Avogadro's rule or Avogadro's law, that if two gas samples have the same number of particles in them, they would occupy the same volume or the same amount of space, given that they're at the same temperature and pressure. You should recognize from your experience with balloons and gases that if you heat up or cool down the balloon, it will change its volume. Or maybe not as familiar, if you're at different pressures. So if you have a balloon that is at sea level, or you take that same balloon and go up to a mountain, it will change its volume. So the two gas samples with the same number of particles need to be at the same temperature and pressure. To make this simpler, there's called a standard temperature and pressure. Standard temperature and pressure means that the gas sample is at 0 degrees Celsius, which is the freezing point of water, and standard pressure is 1 atmosphere of pressure, which is the amount of pressure that you experience from the atmosphere at sea level on Earth. And the molar volume of a gas is that 1 mole of any gas, so long as it is at standard temperature and pressure, will occupy 22.4 liters of space. And so what that means is that in 11 2-liter bottles of gas, like if you had emptied out soda from 11 2-liter bottles, the number of molecules of gas in those 11 2-liter bottles is 1 mole, is 6.02 times 10 to the 23rd. What we'll look at next are mole conversions. That would be converting different things, different substances from units of grams to units of moles, or vice versa. Now, mole conversions work the same way as regular conversions. You just have to remember what things are equal to each other. That 1 mole of something equals 6.02 times 10 to the 23rd power particles of that, which equal 22.4 liters if it's a gas of space, and it equals the molar mass in grams. For one-step conversions, we would be changing particles, liters, or grams into moles, or vice versa. So for example, if we were taking a number of particles, like atoms, and converting it to moles, it would look like this. We would start by writing down our number and its units, and then a time sign and a line. We would put atoms on the bottom, and what we want, moles, on the top. And then we look back to our equalities here, and for moles, you can see that it's equal to 1 mole is this many particles, atoms being a type of particle. And so what we would do, we'd have to be careful to put this into our calculator correctly, but it would be 5.23 times 10 to the 24th divided by 6.02 times 10 to the 23rd. If instead we were trying to do the opposite type of problem, where you were starting with a number of moles and figuring out how many particles there would be, it would look like this. We would start by writing down our beginning number with its units, and then a time sign and a line. We're looking to get a number of atoms, and we look back at our equality that for moles and particles, of which atom are a type, you can see that 1 mole is equal to this many particles. And so you would calculate this by saying 5.00 times 6.02 times 10 to the 23rd, divide by 1. Next, we'll look at volume of a gas in moles. Now, technically, every problem where you would use this equality needs to state that the gas is at standard temperature and pressure, because that gas would occupy a different volume of space or have a different number of particles if it were at a different temperature or pressure. And so this usually confuses students, but it really just means that if it's at STP, you can use this equality, that 1 mole equals 22.4 liters. So you can see I've started off by writing down the number that I'm converting with its units, a time sign and a line, the units I'm getting rid of on the bottom, and the units I want on top. And then the equality, moles and liters, for a gas at standard temperature and pressure. above here, 1 for mole and 22.4 for liters. And so to solve this, I would have 2.81 liters times 1 divided by 22.4. This can be done the opposite direction if we're starting with a number of moles and converting it to liters. So I've set everything up. It's important to remember to include your units when you're starting off. Don't get careless about it, because including your units makes sure that you're going to put your units in the correct place here. If I just put 1.87, I may have made the mistake of putting liters on the bottom of this fraction and moles on the top, in which case I would have been dividing instead of multiplying. And now to solve this, it's 1.87 moles times 22.4 and divide by 1. And last, we'll look at mass in grams and moles. So this, we're going to take a mass in grams and convert it to moles. And it's important to note what substance it is. And so in the units, I've put not just grams, but that it's grams of sodium. Now we'll look back up to our equivalencies. That 1 mole is equal to something's molar mass in grams. For an element like sodium, the molar mass is simply going to be the atomic mass that's on the periodic table. And so to solve this problem, it would be 10.5 grams times 1 divided by 22.99. If it gives you the name of the substance in the problem, it's a good habit to get into to include that in the units, that this is moles of sodium. You'll see when we do more complicated problems further on in the year that you might be calculating moles of different substances, and so it's important to write after them what substance that was. Next, we'll look at one where we're taking moles and converting it to grams. So I've set this up with our number that we're starting with, including the substance to which it's referring. The units will go on the bottom of the fraction, and the units we want to end with, grams, will go on the top. Again, the equivalence is that 1 mole is equal to something's molar mass in grams. And so for the element sodium, it was simply its atomic mass. But now, for 1 mole of water, we need to know the molar mass of water. And water is not on the periodic table since water is not an element. What we would do is we would add in the atomic mass of oxygen and 2 hydrogens. So I showed my work how to calculate the molar mass of H2O. The 2 and the 1.01 would be the 2 atoms of hydrogen, plus the 16.0 is the atomic mass of oxygen, with a sum of 18.0 grams per mole. For our last one-step conversion, we're going to still do a mass with grams and moles, but we're going to use a more complicated substance compound. The reason this is more complicated is because the formula for magnesium nitrate has parentheses embedded in. And so there is 1 atom of magnesium, there are 2 atoms of nitrogen, and there are 6 atoms of oxygen that we would add together for the molar mass. So I'm going to need to calculate the molar mass of magnesium nitrate. I'm going to show that down here and then put that into the numerator of this fraction. And so I get that when I have 1 magnesium plus 2 nitrogen plus 6 oxygen, that it would be 148.3 grams per mole. And now finally I can complete this problem. 0.211 times 148.3 divided by 1. Next we'll look at some two-step conversions. Now, a two-step conversion is going to need to be done anytime you're going from grams of a substance to particles or liters or any of those units from one to another. And you would go through moles. You would first convert it to moles and then change it to your final unit that you want. So here in this problem, 10 grams of CO2 will be weighed out as dry ice, a solid, and you let it become a gas. And that gas, how much space would it occupy at standard temperature and pressure? So our general strategy will be in two steps. First, convert the given units to moles, and then change moles to the desired units. We have 10.0 grams of CO2 to start off. The relationship between moles and mass in grams is that 1 mole is equal to something's molar mass. And the molar mass would be adding the atomic mass of all atoms in the substance, 1 carbon and 2 oxygens. And we get that CO2 has a molar mass of 44.0 grams per mole. Our next step is to convert moles to our desired units. In this case, our desired units are liters. Moles will go on the bottom as a unit to cancel out, and we would be left with liters. The relationship between moles and liters of a gas at standard temperature and pressure is that 1 mole is 22.4 liters. This is set up now, and our units cancel out correctly, and the way to calculate this would be 10 times 1 divided by 44 times 22.4 divided by 1. And we get an answer of 5.09 liters of space. We'll do one more example that includes a number of particles. Again, we'll start by taking our given units to moles. I've put liters on the bottom so that they will cancel out, and moles on the top. And these are the equalities. Next, converting moles to our desired unit, which would be atoms. And the relationship between moles and atoms, remember, could be generally said to be particles, and that's 1, and then Avogadro's number, 6.02 times 10 to the 23rd. And the way to calculate this would be 1.8 divided by 22.4 times 6.02 times 10 to the 23rd. And we get a final answer of 4.8 times 10 to the 22nd power atoms of helium. Well, that's moles for you. I know that at first glance or at first try, they can be a little bit confusing. But hopefully with enough practice, you'll see how they can be useful and how this concept can help you relate things that are too small to measure and see, like atoms and molecules, to the things that you can measure about a substance, like its mass or its volume.